Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is component testing and oxygen sensors. So this is another one in our series that we're doing now on component testing and focusing on one component per session here. So this time, oxygen sensors. We're going to talk about a couple different types. But when we talk about oxygen sensors, we can't forget about fuel trims, right? Because fuel trims and oxygen sensors go hand in hand together. So quick on fuel trims and how they relate. So what is fuel trim? Well, fuel trim is a window into what the computer is thinking in order to keep that vehicle running the way it's supposed to. Now, normally a vehicle wants to, or at least an engine, wants to see 14.7 to 1 air fuel ratio. So 14.7 parts of air to 1 part of fuel. So that's ideal. And the computer wants to try and keep it that way. When the oxygen sensor is the first line of defense. So it's in the exhaust stream. And as the name says, it detects oxygen in the stream. So if it gets a lean condition, so that would mean excess oxygen, more oxygen that's supposed to be in that exhaust stream than normal, it will send a command to the computer and say, okay, I see way too much oxygen. We don't have enough fuel. So we need to add fuel so that you get a positive fuel trim number. So that'd be your short-term fuel trim feeds to long-term fuel trim. So I get a positive fuel trim number. Then it will add fuel as a percentage. And then eventually it's going to go too far and say, hey, whoa, now I got too much fuel. I got a rich signal. So I don't have enough oxygen. I'm not reading as much oxygen as I want to. So now we're too rich. So then it sends another command to the computer and says, well, now we need to do a negative fuel trim. We need to pull that fuel back, and we need to lessen the amount of fuel. So that's a negative fuel trim, right? And then it pulls it back, and then it gets a lean condition, and then it adds it, and then it gets a rich condition, and so on and so forth. So by design, generally speaking, on many vehicles, it is just that back and forth, right? The oxygen sensor goes rich, and then the fuel trim goes lean. The oxygen sensor goes lean, the fuel trim goes rich. It's not really a rich lean, so to speak, but it's an amount of oxygen content that it's measuring. So first off, we'll start with the, I guess the classic, the zirconia sensors, right? So we have the couple different types. There's many different variations on this subject out there. I remember, back the 80s model GMs, they had that little single wire that was pretty universal. It was just kind of sat there in the front, and that's what you had. And then, of course, we have fairly newer designs where you also have the heater circuit in there as well. So this has a signal wire, two heater circuits, and a ground, right? So there's different variations on it, but they all work pretty much the same when it's a zirconia sensor. So a zirconia sensor could be heated or unheated depending on the way it's designed. I mean, nowadays it's gonna be pretty hard pressed to find an unheated one, but by and large they are all heated now. But hey, you could be working on an older vehicle with an unheated one, but it works the same way. So what it does is it produces a voltage. That's how we can get that one wire signal wire that goes back to the computer, because it does generate a voltage when it detects oxygen ions between these electrodes here. So we have the exhaust gas here, and we have the reference air out here. So all the oxygen sensors need an outside reference for what the oxygen content in the air outside is. So oftentimes you'll see like maybe little slits in the back. I know I was reading on one GM one today where it actually comes down the harness and one of the wires. So it does need that reference air, and you want to make sure that it has that. But then it measures the difference and it generates a voltage based on the difference between what's in the exhaust gas and what's in the reference air. Now, the range of this is going to be roughly a little higher than 0 volts, maybe a tenth of a volt, something like that, up to about 900 millivolts, sometimes a little bit higher. But roughly 0 to almost 1 volt is what that's going to put out. It is most accurate at the midpoint, which is coincidentally 14.7 to 1 oxygen to fuel content. So 455 millivolts is about halfway between 0 and 900, right? So that is our halfway point. That is our stoichiometric air fuel ratio. So that's kind of how that works. It generates a voltage that goes up and goes down. Now, as we said, ideal air fuel ratio is 14.7 to 1. And if we look at this chart over here on my voltage, halfway in between 14.5 to 1 and 15.4 to 1, that's right about 14.7. So we get 455 millivolts, which is positioned somewhere in there. The most accurate range of that sensor, and that is in a narrow band of voltage. That's why you may have heard it referred to as a narrow band oxygen sensor, right? So if we look, the higher voltages are on the rich side, and then the lean is on the low side. So rich is high, low is lean on these zirconia sensors. Now remember, as I said before, a zirconia sensor does not sense rich or lean exhaust. It's kind of a confusing point there. It's a little bit of a misnomer. It's actually just it's sensing oxygen, right? It's an oxygen sensor. That's what it does. It senses oxygen. So we can either have all oxygen is used up, so I don't sense much oxygen in this exhaust flow. So that's your high side. That's your rich mixture, 900 millivolts. And then some oxygen is left over. I have excess oxygen, more than expected. That gives me a lean condition on the engine, and that's around that 100 millivolts. So remember, rich is high, low is lean. And a typical sensor output, if I were to check this with a with a scope and check and see how it's cycling back and forth, low to high, I want to see voltages in those ranges, over 800 and below about, maybe 200 millivolts down to, we're almost around about 1 millivolt down here. So you can see how it goes up, it goes down, it goes up and down. It should cycle back and forth at an idle. It'll change the cycling depending on the air fuel mixture in the exhaust. So if it's just sitting at an idle, just running normally, we should see it cycle back and forth. Now there's a set number of times it should cycle back and forth. We'll talk a little bit more about that in a little while. So you can check the up and down, and they call that the rise time. How long does it take to rise and how long does it take to fall? And if it falls out of specification, that's what we call a lazy oxygen sensor. If you've ever heard that term, it takes too long to react to the change. So then maybe it wouldn't be so sharp straight up. Maybe it'd be over a little more. It would take a lot longer, look a lot more fluid, more lazy, going up and down, as so to speak. So that's the sign of that the sensor is wearing out and it's not able to detect oxygen as quickly as a new one would. So let's take a look at how we might examine a vehicle that has a problem using oxygen sensor. This is an 07 GMC Sierra, came in, engine light on, and complained of a whistle under a load. All right, so it made a weird whistling noise under a load, and we have an engine light on. So pull it in. First step, of course, is we want to check the codes. Looks like we got 2 codes in there. Engine and transmission tend to share on this. So we got a P0171 lean condition and a P0300 misfire code. Those are the super fun ones, right? It's lean. Okay, why is it lean? Could be 100 things. Where is it misfiring? Why is it misfiring? I don't know. It could be a lot of things. Probably misfiring because it's lean, but it doesn't tell me where, right? It just says there is an engine misfire detected. It doesn't say cylinder 1, cylinder 5, what have you. It just says, hey, we got a misfire. So we want to take a look at that. And of course, the lean condition, those are kind of a pain to diagnose as well, just because it could be, there's a laundry list of problems that could be. So let's see if we can find some information to help us on this. So on this case, we're looking at a Zeus. So Zeus has intelligent diagnostics. We can just click on diagnose. This will just make it a lot easier to access all the information for this problem. And that's what intelligent diagnostics does. If you've heard of intelligent diagnostics, but maybe you're not aware of what it does, it takes the information available for the vehicle filters it down based on certain topics of information and based on that vehicle and that code at that time. So for a PO 171, it will return all the information only for a 171 on this 07 Sierra. There's 4 TSBs in here. For essence of time, I'll just tell you ahead of time that none of these applied to our particular situation. We looked through them, none of them applied. Over here is our top repairs graph. So this is based on real world data over 1.3 billion real world repairs to tell us what fixed the vehicle in this situation. So this vehicle had about 75, 80,000 miles, somewhere in that neighborhood. So it was right around here. So if I were to look at this mileage, because it's mileage based, number one repair at that mileage time is the oxygen sensor. And then manifold gasket and the fuel filter are tied down here and so on and so forth. You can see it kind of gets a little spaghetti looking as we go, but being able to use the mileage to tell us where things are, well, that's a big help too. So at this case, maybe we're looking at the oxygen sensor, maybe not, hard to tell, but these are the common suspects. So come down here next to smart data. And what smart data does is out of the hundreds of PIDs that can possibly be available, filters them down to just what we're looking at. Also sets these monitoring flags on some common failures. So MAP and mass airflow, those are also could be common indicators for a lean condition. But in my case, in this case, we want to look at those oxygen sensors because we're talking about oxygen sensors tonight, right? So that's why we're doing this. So we'll go in and look at oxygen sensors. We got our voltage, heater circuits. Let's see what we got. So we're looking at oxygen sensors, and these are the front over here, and these are the rear oxygen sensors over here. It's 4 sensors on this vehicle. Now we have on the bottom our good bank, the one that's not giving us a code, right? PO 171, that's bank 1, 174 is bank 2. So we see we do not have much of an issue if we know what we're looking at. So up and down, 800 millivolts, about 69 millivolts, right? It goes up and down, cycles back and forth the way it's supposed to cycle back and forth. If I wanted to correlate this with my short-term fuel trim, you see they kind of chase each other around. One goes up, one goes down, right? So we can see the difference in the fuel trims, and that's 0 to 5%. So that's normal on that side. Bank one sensor one, we'll see it also switches back and forth. It also goes up and down in about the same range, right? 61 to 890, 69 to 868, pretty close, right? So it cycles back and forth, but if you look at the picture, there's a lot of other nonsense going on here. You see how it's not that smooth picture like we have down here. We got a lot of ups and downs, a lot of fuzzy, maybe it's noise, hard to say. Looks like it's just being really, really sensitive, really overreacting to whatever's going on. Okay, so that might be a problem. We need to dig a little bit deeper, but that could be a problem. If we look at the rear O2 sensors after CAT, the bank 2 stays kind of in the middle, and then it goes down a little bit, stays in the middle, still goes down. So that's fairly normal, I guess, for what we're looking at there. That looks okay. And we see the bank 1 where we have the problem. It does also stay fairly flat, goes down, stays fairly flat. But if we look at the range, we're not at 500 something volts or millivolts. We're at 156 at the most, which is over here. So 156 to 74. So that is stuck towards the lean side, because remember, low voltage on a zirconia sensor is lean. So this is actually why we were called to kind of take a look at this truck. It's like, I don't know a ton about oxygen sensor readings, but that doesn't look right to me, is what the text said. So I said, well, let's take a look. And sure enough, yeah, that is definitely on the lean side for sure. And it's staying there. It's not going back up at all. Definitely on the lean side. So we took a recording of the data and opened it up. And this is what ShopStream Connect looks like. And just had a little bit more organized. We're able to see a little bit more on the screen here. So bank 1, bank 1, bank 2, bank 2, short term on bank 1, long term on bank 1, and so on. So once again, still have that same look, right? Normal on the bank 2. Bank 1's going up and down, but we got all this fuzziness, weird stuff. Rear O2 sensor doesn't get over 156. Rear O2 sensor on the good side is about half a volt down to a little bit. Short-term fuel trim bank 2 looks good. Short-term fuel trim bank 1, once again, gives us that same type of weird up and down vibe. Also note, here's another key point. So remember how we talk about oxygen sensors driving the fuel trims. My oxygen sensor over here on bank 1 is driving this fuel trim or this fuel trim is being driven to a lean condition. So it's a rich, positive fuel trim. It's adding fuel to correct for the lean condition that the oxygen sensor is noting, right? We see a lot more activity here, there. So it's 4 to 10%. 10%, rule of thumb, when you get to double digits, there's something wrong with the car. We need to kind of take a look at that. Now, if we look at the side that's not giving us trouble, we see it's 0 to 5%, which is normal. Should go 0 to 5%, maybe a little bit negative as well, just kind of back and forth. So that short-term fuel trim is pretty high. Long-term fuel trim is pegged at 25. Doesn't go over 25% anyways. So it's just been at 25% since we turned it on. It's been going this way for a while. So the other rule with fuel trims is this will tell you, short-term fuel trim tells you what's happening now. Long-term fuel trim tells you what's been happening over the last period of time. So 25% stuck on full. We're putting as much fuel in here as we can possibly muster, and it's still not fixing the condition. So looking at all this, judging this, we can see that if we look at the front oxygen sensors on the top left here, they're both cycling back and forth. I think we can agree that. But that one looks weird. Looks like it's got a lot of activity. So to me, combustion is still occurring normal because they are cycling back and forth, and they're fairly similar in look. But we got all this extra activity, and then the rear sensor has a lot of extra fuzziness, and it's stuck on the lean side. So it seems to me, just by looking at this, that it's being extra oxygen is being introduced after combustion. So what might cause extra oxygen to be introduced after combustion? That's one thing that could. Just took a look down there on the side of the engine, and sure enough, had aftermarket headers on it, by the way, aftermarket exhaust. And they pulled that off, say, well, it looks like it's cracked, and sure enough, it was cracked. So that could be also the whistle under load. So we think about it, everything was tight on the vehicle, right? So the flange was tight, and it's cracked right at the flange. So it's still going to have a pressure on it. So under pressure, under load, that exhaust gas is going to try and push its way out, right? So that might give us a whistling noise like that. What's it doing at idle? At idle, we don't have that pressure pushing out. We have the acts like a venturi, right? So we have the exhaust gas going through the pipe, and then it's going to act like a venturi and suck in around that crack extra air. What's the first thing that air runs into about 3 inches down the pipe after the other side of the flange is our front oxygen sensor. So that's the first thing that says, oh, well, I'm lean, so I need more fuel. And then if it goes like that for long enough, then it throws a lean code because it just cannot fix it, right? So we have this exhaust leak right here at the clamp. So they simply, give a little bead of weld on there, fix it up, bolted it back together. And that solved the problem. But let's just quick verify as well that we verified or that the oxygen sensor is working, because it was giving us some weird readings, kind of led us to that. But let's see what this oxygen sensor is doing voltage wise after the repair. We'll go on a component test. We have since this is intelligent diagnostics, we have the specific to the code component test right there. Oxygen sensors number 1. Go in there, pull up the test. The nice thing about guided component tests, if you haven't seen that either, that's available in any Snap-on tool with scope. It is going to show you the pin assignment for the component you're testing. It's going to be this one. It's a 6 liter. It'll give you the pin assignment. It'll tell you where to hook up the color-coded leads. Yellow goes to the oxygen signal. O2 signal. Black goes to no good ground. All right, so it gives us that information. It tells us how it should work. So it should be over 800 millivolts, below 250 millivolts at 200 RPM. Should cycle 3 to 5 times in 5 seconds or 6 to 10 times in 10 seconds. And then we'll snap the throttle several times and observe. So we just checked that out in idle just to make sure that it went back and forth and did what it was supposed to do. So we have view meter. When we hit view meter, it sets the voltage range where it needs to be, and it sets the time base where it needs to be. So quick and easy, just hook it up to where it tells you to hook up, and you're good to go. So I see around about 800, down to around 200, below 250, cycling back and forth. 1, 2, 3, 4, 5, 6, 7, 8, 9 times in a 5-second window. So that's cycling normally. It's doing what it's supposed to do. It's supposed to go back and forth like that. We don't see any of that weird noise or fuzziness. We don't see any weird dropouts, nothing like that. So that is a fully working oxygen sensor. So there's nothing wrong with the oxygen sensor on that. And we were able to tell by looking at the data, which is pretty cool. And then we could also verify with the guided component test as well. So if we wanted to take a road test and verify with the data as well, we'll see now there's bank 1 over here, bank 2 over there, and we can see how it cycles back and forth. I don't have any of that weird stuff going on. Short-term fuel trim never gets over 4, never gets over 5, actually goes negative for a period. Long-term fuel trim on both goes down to 0. So we can just by a road test and verify on the data that way, we can see it as well. All right, so that's zirconia sensors. Now let's talk about AF sensors. So AF sensors are the newer kid on the block. They've been around for a while, decades, but they work similarly but differently than a zirconia sensor, and it's, as such, we need to test it differently. So what a wideband air fuel ratio sensor is, it's basically 2 zirconia sensors together like a sandwich, and then in between, in the middle of that sandwich, we're going to have a monitoring chamber. So there's really 3 chambers in here. We have our reference air on the outside, we have our exhaust gas on the inside, and then we have a zirconia membrane there, and there's a zirconia membrane there. So it's like 2 oxygen sensors. In the middle, it's going to be my monitoring chamber, and the computer will try its darndest to keep this at a lambda of 1. So if you ever heard people use the term lambda of 1 equals 14.7 to 1 air fuel ratio. So your normal, where it's supposed to be, right? So lambda of 1, higher and lower is outside of that range. So it always wants to try and keep this at a lambda of 1. And then this will measure as a normal zirconia sensor would, and tries to put out, which the computer tries to keep it at that 4.5 volts, 4.455 millivolts in there. They are heated as well. So as I said, it's like a sandwich. The AFR sensor uses an entirely different operating strategy, though, than that conventional zirconia sensor we looked at earlier. So one cell is used to measure the oxygen content in the exhaust stream. The other is supplied with a very small electric current from the PCM. So in here, it's capable of moving oxygen ions through this gap in a positive or a negative direction. So if I do positive current, it flows one way. If I do negative current, it flows the other way. So it does this, and it's very, very small, like milliamps, very, very small changes in current that change the direction of that oxygen flow to keep this at lambda of 1. So it wants to keep that stoichiometric ratio between both cells, keep it as 1. So this is known as a pumping cell, and that is your measuring cell over there. So it measures and wants to make sure that that is at 1 at all times. Based on that, the computer will do a calculation, and it will decide how much oxygen is in the exhaust. It works over a much wider range. So that's why you may have heard of a wideband AF sensor. Works over a much wider range, and the computer does a lot of the calculating for you. Really, really hard to judge this amperage. As I said, it's very, very small changes. Really hard to tell. Pretty much to get it, you would have to crack open the wire, and we wouldn't want to do that. So just the way to diagnose these is to use the PCM. All right, so PCM monitors that varying current that it puts into the pump cell, and then the PCM converts that into a voltage pit. So I will see a voltage pit in my data stream. So the best way to test the signal is by monitoring that voltage pit. Now it is possible to monitor the varying current, like we said, but it's very, very small changes. You need like a micro amp clamp in order to do it, and it's very difficult. Also note that an AF sensor works the opposite of a zirconia sensor when it comes to looking at the voltages. So when it becomes richer, O2 zirconia sensor goes up. Remember how we said rich is high? And then when it's rich on an AF sensor, it goes the other way, it goes low. When the exhaust is lean, AF voltage goes high, oxygen sensor voltage goes low. So they're opposites of each other. So to display that, here's a little screenshot from a test we did for another class. This vehicle has an AF sensor in the front and a zirconia sensor in the back. So we should be able to see those different voltages here. Now, AF sensor, when things are running normally, this is just at a normal idle here, should be around 1. Tries to keep that lambda, that air fuel ratio, at a 1. So that we should see 1 volt. All right, that's what we're going to see there. So the 1 volt there. Rear oxygen sensor is a little on the high side because, well, all the oxygen's used up. Once we get through the catalytic converter, we shouldn't have much oxygen left, so it should be on the higher side. But then in this case, we introduced a vacuum leak. So we introduced the vacuum leak. You see that the AF sensor goes up, reacts pretty quick because it's actually like way over here. So it goes up and goes up. And then the rear O2, when that reacts, it's going to take longer to react because it's further down the stream. That goes lean, which is low. Then when we repaired the leak, and you can also see how the short-term fuel trim reacted as well. But when we repaired the leak, the AF sensor reacts immediately, goes down to rich, because now it was pumping so much fuel in there because it was reading lean. Now it's going to read rich. And then the rear O2 sensor goes back up to rich as well, back up there. And then everything kind of stabilizes after a few seconds. So we can see the difference. As we said, AF goes up when it's lean, rear O2 goes down when it's lean. And that's how we can kind of tell by looking at it, the voltages. We can look at the PIDs and we can know what's going on, what it's reading as far as the vehicle. Another difference between the AF sensor and the zirconia sensor is that there's an operating temperature over 1200 degrees. With the heater, they want to heat up really fast. If you're here at the very beginning and watch the video, it takes less than 10 seconds to heat up to that 1200 degrees Fahrenheit. On the zirconia sensor, typically those run 650, 640 degrees is where those want to be. Temperature is very critical on these AF sensors, so oftentimes a special pulse width controlled heater circuit is used for precise heater control. So an example I'm going to show you here in a second on a GM where you have to reset that. So we're going to talk about that right now. Let's go take a look at where we might find that. All right, so we'll take a look at a couple different things on oxygen sensors on the tool. So I'm just going to pull up my scanner here, and I'm going to pull up our trusty old Chevy Tahoe because that has zirconia sensors and that has what I want to talk about. So 2016 Tahoe. I'm going to go in and I'm in demo mode. So there's that. There we go. Okay, so easiest way to find anything I might need to reset or relearn on a vehicle, if I have a tool that supports it, it's going to be my service resets and relearns quick menu right here. Otherwise, I could go into the engine system, look through all the resets, but this categorizes it by job. So if I go in here under engine, that's going to be, and replace and relearn oxygen sensor. So it's really useful if you have this to check in here and take a quick look. Is there anything I did that might need a reset? So did I replace an oxygen sensor on this truck? So you can go in there. It's going to give you our top repairs graph information, TSBs related, and then any functional resets related to it as well. So we see we have an oxygen sensor heater. Let's learn a little bit more about why we need to do this. So if you have repair information, shop key or Mitchell, you can link to it straight from the tool as well. It'll pass your login information through. It'll pass most of the vehicle information through. Sometimes we don't get like LTZ and things like that. And it'll pass the repair we're working on through. So we see oxygen sensors pre-populated. I'm going to go over here to oxygen sensor replace, and it's going to bring me all of my information for replacing an oxygen sensor. So TSBs, real fixes, top repairs, categorizes the information just like Intelligent Diagnostics filters it down based on the search term. Now, let's say I wanted to go in and look at the wiring diagrams. I want to see how it's wired. Maybe I'm going to test it. So I'm going to pull up the wiring diagrams, and you'll see on this, it says I'm on panel 7 of 8. So one of the enhancements to the new wiring diagrams we have in Shopkey and Mitchell is it will go based on your search as well. So it brings you to the panel that has the oxygen sensors on there, and you see they're right at the top. You'll also notice that all the wires are highlighted that are attached to that component that I searched for, which is the oxygen sensor. So if I zoom in a little bit, we'll see that they're highlighted. And then we have a heater circuit, and then we have the sensor circuit. So it is a zirconia heated oxygen sensor. If I wanted more information on the oxygen sensor, I could from here just click, and it opens up a search box for me as well. So I can get all of my different information, component locator, operation, guided component test, which we're going to look at in a second, specs and such. So really everything can be done, or a lot of it can be done right from the right from the wiring diagram. Right? So that's pretty cool. So we got some information there. Another good place to go is if I'm after a repair is to go to after repair. So we go to after repair information. It's going to tell us what we need to do after we're done. And all it gives us is one important warning. So it's caution: when replacing the oxygen sensor, perform the following. A code clear with a scan tool, regardless of whether or not a code was set. So you got to make sure you clear the codes. And an HO2S heater resistance learn reset with a scan tool where available. From the above, in order to reset the HO2S resistance learned value and avoid possible oxygen sensor failure. So what happens is it uses, like we said, that pulse width modulated controlled heater circuit. And it learns. They call it a resistance compensating oxygen sensor heater circuit. As the sensor ages, it's going to heat up, it's going to cool off, it's going to heat up, it's going to cool off, because, you know, turning on and off, heater circuit. As it heats up and cools off, the resistance changes inside the heater circuit. So eventually, you know, the ECM has to learn, and we need to keep it on longer to keep the temperature getting up to where it needs to go. So it learns that over time. Now, if I replace that oxygen sensor when it fails for whatever reason, the brand new oxygen sensor is still going to be getting that amount of amperage. There's a pulse width control, so it's going to be the long pulse width. And a brand new one's probably going to expect level maybe down around here, but it's getting fed amperage about here. So if we're over, you know, putting too much amperage to it for too long a period of time, the heater circuit goes pretty quick. We've had techs tell us, oh yeah, a couple 100 miles they've had it done. And I've also had people tell me, oh yeah, I did it. I changed that sensor 3, 4, 5 times before I figured out what I needed to do. And really all it is a simple reset. We're going to do that right now. But if you don't do that reset, and this is on 06 and newer GM vehicles, so there's a lot of them out there. If you don't do that, you may end up replacing that oxygen sensor pretty quick. So there's an oxygen sensor heater learn right here. If I go back to my scanner, it's going to load up, pulls the functional test from the vehicle. Okay, on the next screen, hit reset, hit continue. Now, of course, this is a demonstration vehicle, so it's not going to have any data on the next screen, but we would see where is the value currently for the amperage. So all I need to do is hit reset, resets them all back to 0, and then they'll relearn back to where they need to go. So if I only replace one sensor out of the 4, the other 3 would learn back to where they need to go, and the new one would learn back to where it needs to go. Everybody's happy. All right, so that's a reset, and that is very important. And those are on zirconia sensors, not even the AF sensors. Some more information. If you go into guided component test, if you have a tool with guided component test, before I load a vehicle, because it is VIN specific information, before I do that, there's also built-in training and classes inside the tool. And if I go to how to, and I go all the way down to the bottom, there is a category for test tips. So if I go into test tips, there's one right here, zirconia oxygen sensor rise times. This will tell us how those zirconia sensors work. So it's going to tell us how to set up the meter to do a test on it. Let's see. So run the engine at 2,500 RPM for at least 3 minutes to make sure the oxygen sensor is at operating temp. We'll induce metered propane in the intake until oxygen sensor is above 0.8 volts, which is rich. Shut off propane and observe the oxygen sensor signal. When the signal drops below 0.175, quickly snap the throttle and release, and the voltage rises above 800 again. Then we'll look at the recording. We're going to measure with the cursors. We're going to go through and see what the distance is. And the delta time from one side to the other for how long it takes to go from bottom to top is what we're going to see. So a good oxygen sensor typically will switch between 0.175 and 0.800 volts in less than 100 milliseconds or 0.10 seconds. Right, so to be able to read that and you can see where's the bottom, where's the top. So if you remember that signal I showed you before, there's the bottom, there's the top. How long does it take to get there? It should be less than 100 milliseconds to get to the bottom than the top. Now, if I wanted to do it from here, I can just hit view meter. It's going to open the meter for me automatically, and it's going to set it up for me and tell me what I need to do there as well. All right, so that is zirconia sensors. Let me look at one more thing. Let's go into a Toyota 16 Camry with a 4-cylinder. All right, so on a Camry, many Asian cars, has an air-fuel ratio sensor. So I go to air-fuel ratio sensors and we go to component information. It's going to tell us how it works. So once again, it tells us that about that reference cell in the middle, pumping cell with a current, and wants to keep that reference cell at a lambda of 1. When it is 1, there will be no current applied to the pumping cell. So that's we're talking about that amperage in there. The amount of current supplied is proportional to the amount of oxygen in the exhaust gas. ECU uses that amount of current as a signal. ECU uses the signal to calculate the actual air to fuel ratio. The injection duration is altered accordingly. So it reacts very, very quickly. And as we said, output is opposite of that seen with a conventional O2 sensor, higher voltage under lean conditions and lower voltage under rich conditions. AFR sensor is faster and more accurate than a normal zirconia O2 sensor. Note, the sensor signal lines are biased to about 2.9 to 3.3 volts. So you should see some sort of voltage on the signal wire somewhere in that 2.9 to 3.3 volt range, at least on this vehicle. All right, so then we have a wealth of information over here. I'm not going to read through all of this. If you have one of these tools, you can definitely check that out. But not able to read amperage with this, but we do have this heater test. We can test the heater circuit for duty cycle and such. And then actual sensor tests as well. We have a quick test and a reference voltage test. So quick test, this is going to have us disconnect the sensor, jumper wires to the heater terminal so the heater still works. And we'll start the engine, hold the steady RPM until it stabilizes. We can snap the throttle, and then we should see a fast response. Voltage should decrease during open throttle and increase during decel. The shape is less important than the fall and rise action during snap throttle test. Test may set a pending code as well because, hey, I got it on phone. Right, so there's a few different tests that we can do on our different sensors, and there's a ton of them in here inside guided component test if you have a tool with that capability. If you don't, well, you can still test it using a scope that way. We could also go into the scanner and test the AF sensor voltage that way as well. And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.